Hey there, student physicists. How are you? It's Miss Persad again, so you know that means we are going to do our read aloud. As always, if this isn't helpful, you don't have to use it, but if it is helpful, let's get started. And feel free to leave me comments about what I can do better and make this even more helpful for you in Google Classroom. All right, I'm going to share my screen with you, and we're going to get started. I need this to move. Okay, so as always, when we are doing any kind of reading, we want to make sure we read the headings and subheadings. So the first thing we're going to do is read the heading, which is comparing series and parallel circuits. After that, our subheading is the language of electricity. So these are the two things that are going to help you decide where you should be reading when you are answering your text-based questions. So today I'm going to try something a little bit different. I'm going to read through the entire passage, and then after I'm going to go back and do some explanations. So then if you only require the reading, then you will just get the reading first and you can stop. And then if you want to hear the extra explanations at the end, you can get that after I finish the reading. Okay, let's get started. So comparing series and parallel circuits. Paragraph 1. In series circuits, all the coulombs of charge travel through the first light bulb, then the second light bulb, and then the third light bulb. The electrons require a complete circuit or pathway from the battery to the light bulbs and back to the battery to flow. If one of the light bulbs is broken or removed, then the circuit path is no longer complete and there will be no flow of charge or current. All of the light bulbs will go out. Paragraph 2. In parallel circuits, some of the coulombs of charge go through the first light bulb, while other coulombs of charge go through the second light bulb. And still, other coulombs of charge travel through the third light bulb. Each light bulb has a complete circuit or pathway from the battery to the light bulbs and back to the battery. If one of the light bulbs is broken or removed, then the circuit path to the other light bulbs is not affected. All of the other bulbs will continue to light. Paragraph 3. If the battery provides 6 volts and the circuit contains 3 resistors in parallel, then each resistor will get 6 volts of energy, but only from some of the charge. The total voltage provided to each of the resistors is equal to the voltage of the battery, 6 volts. That is because all of the energy of the coulomb of charge is given to only one resistor. Paragraph 4. Because each coulomb of charge goes through only one resistor, then the current leaving the battery is split among 3 resistors. If the current leaving the battery is split amongst 3 amps, 3 coulombs per second, then each resistor gets 1 amp of current for each identical resistor. This means that 1 coulomb that passes the first resistor every second will drop 6 volts there. The same thing will happen at the other 2 resistors. Our subheading here is the language of electricity. Paragraph 1. A formal study of physics requires us to use some of the basic language of electricity that was introduced in this and previous sections. The terms to which you are introduced in the previous sections are shown in italics. Bullet point number 1. There are 2 kinds of electric charge, positive and negative. Protons, which have a positive charge, and electrons, which have a negative charge, are the source of these charges. Bullet point 2, like charges repel and opposite charges attract. Bullet point 3, there is a smallest amount of the property called electric charge, the amount possessed by one proton or one electron. While protons and electrons differ in several ways, such as mass, an electron and proton have an identical amount of charge. Bullet point 4. Electrons move in electric circuits of the kind you have been exploring. They carry the electric current as they flow through the circuit path, delivering energy that is transformed into light and heat by the light bulb. Protons, although present in the materials from which circuits are made, do not flow because they are locked within atoms. Number 5. Scientists have agreed that upon standard package of electric charge called the Coulomb, the charge of a single proton or electron is 1.6 times 10 to the negative 19 C. In order to get a single Coulomb of charge, it would take 6.25 times 10 to the 18th power electrons, or 6.2 billion, an amount equal to 1 over the charge of the electron. 1 Coulomb is approximately the charge transferred during a lightning bolt. Scientists have agreed upon a standard rate of flow of the electric current in circuits. When 1 Coulomb of charge passes through a point in a circuit during each second, the current is said to be 1 ampere, often abbreviated as amp and written with the symbol capital A. Different materials offer different electrical resistance or opposition to the flow of electric charge through them. That is what the word resistance means: opposition to flow of electric charge. A material in an electric circuit that offers resistance is called a resistor. Tungsten, from which light bulb filaments are made, has high electrical resistance. When electricity flows through a light bulb, for instance, the part that glows is a metal called tungsten. It robs energy from the moving electrons, gets hot, and glows. Copper, by contrast, has low resistance. Electrons transfer very little energy when flowing through copper. That is why copper wire is used to conduct electricity in electric circuits. Electrical resistance is measured in ohms. The symbol for an ohm is the Greek letter omega, and this is what it looks like. Last bullet point. Batteries or generators provide energy to the electrons. These electrons are then able to light bulbs, heat wires, or make motors turn. The energy given to each Coulomb of charge is measured in volts. And so that's the entire reading. I'm going to go back now and give you maybe a couple details and clarify a couple of things that I think could be helpful. So in a series circuit, so series is the one where from the battery, everything kind of goes in a circle. So series circle, right? So here in a series circle, in a series circuits, all of the energy that the coulombs get from the battery are shared. So when you go to one light bulb, let's say there's 3 light bulbs in this circuit. Let's say you have a 6-volt battery, right? So when this Coulomb has 6 volts, goes to the first battery, it's going to give 2 of its volts. Then it's going to give 2 of its volts here to the second one, and it's going to give 2 of its volts to the third light bulb here. 2 plus 2 plus 2 equals 6. And that's how many volts the battery gave the Coulomb of charge. So in series, you want to remember you share the energy, you share, right? And so we also want to remember that coulombs are carrying the energy. The Coulomb of charge is not used up. The energy is used up, right? The volts, and then it goes, it moves, and it gives the battery the joules of energy. Now, in parallel circuit, you see the 2 L's like this, right? I like to think of the L's in parallel like lines. I want you to think that you're at Stop and Shop, okay? And your line is moving and somebody else's line is not moving. Does the fact that their line not moving, does it affect your line not moving? No, because you're in 2 separate lines, right? So each Coulomb of charge goes to the battery. They pick up 6 volts, right? But now, instead of traveling in a circle like series, it travels to its own individual line. So one Coulomb of charge goes to this light bulb, and the other Coulomb of charge goes to this light bulb. And if we added another lane, let's say another lane at Stop and Shop opened, well, guess what? They would go to their own line. So the Coulomb of charges go to different lines to get to the light bulb. So each circuit, each light bulb gets the full amount of volts, okay? So if you have a 6 battery, if you have 6 volts, a 6-volt battery, each light bulb is going to get 6 volts. This one gets 6 volts, this one gets 6 volts, and this one gets 6 volts, okay? Because each Coulomb of charge is going to their own line, just like you would do if you were shopping. So that brings us back to one other point. In series, remember, series is in circle, and in series we share, right? So in series, it says here, if one of the light bulbs is broken or removed, the circuit path is no longer complete, and the light bulb will go out. So in series, you require all of the light bulbs to be working in order for them all to stay on. If you've ever used Christmas lights and you've noticed that one of your lights is broken and the rest don't work, that's because your Christmas lights are often wired in series. So if any part of the circuit is broken, that means it's not a complete circuit and all of the light bulbs will go out. Okay, so in series, because you share, you need a complete circuit or else all the light bulbs go out. Now, in parallel, when we have 3 different lines, right? If this light bulb stops working, it doesn't matter because this light bulb is getting its own source of energy, and so is this one. The coulombs of charge have their own lines. So even if this one is not working, that's okay, right? Just like we were saying, if one line at Stop and Shop is not moving, does that affect your line? No, it doesn't. So in parallel, because parallel, they have their own lines, they have their own complete circuits, it does not matter that this light bulb is not working. The coulombs of charge are still able to deliver their volts and their energy to their individual batteries. I meant their own individual light bulbs, okay? So the big differences that we want to remember here is that in series you share, in parallel you have your own individual complete circuits or lines, okay? The other thing is in series, that means if one light bulb goes out, they all go out. In parallel, if one light bulb goes out, that's okay. The rest do not go out because they have their own lines. So in your house, do you think that your house is wired in series where one light goes out, all go out? or in parallel, where if one light goes out, the rest of the house still stays illuminated. That's just something to think about. Also, here in our fourth paragraph, it says that it is talking about resistors. It's split amongst 3 resistors. Now, in our reading, it said that tungsten is the filament that is found in our light bulbs, okay? So when they are saying resistors here, another word for resistors that we can change this with is light bulbs, because they are slowing down or opposing the flow of the electrons. So if changing the word resistor here to light bulb is helpful, then go ahead and do that. A couple things we want to touch on. The two types of electric charges that we have are positive and negative. Protons match the P, right? P, positive proton, and electrons. Electrons are negative. And if you remember all of the investigate that Miss LS has been doing, it is the electrons that move, okay? It says here that the reason protons don't move is because they are locked within atoms. Do you know where in the atom the proton is locked? If you said the nucleus, you are right, okay? So last thing about charges, like charges, like means same. So positive and positive, repel. Negative and negative, repel. They don't want to be close to each other. Negative and positive, attract, okay? So you remember, like repel and opposite attract. The other thing you need to know is electric current is an ampere, okay? The movement of how fast the electrons are moving in a circuit is called the current. And current is called amperes, is measured in amperes, okay? So that is how fast 1 coulomb of charge, remember the coulombs of charge are carrying the energy to the light bulbs, right? Carrying the energy to the appliances, right? How fast they are doing that is the current. So how fast per second a coulomb moves past a certain point is the current. And that is measured in amperes. And sometimes we just say amps, right? And that is symbolized by a capital A, okay? And so resistance, we talked about that a little bit earlier. Resistance is opposition or something that makes it more difficult, right? So a resistor is providing resistance. It is making electricity more difficult to flow through, okay? And so that's what we said. Tungsten, from which the light bulb filament is made, has high electrical resistance. When electricity flows through the light bulb, for instance, that part glows, okay? So when we're thinking about it glowing, I know that Miss LS did an experiment where she used steel wool. And you have to think about, how is the steel wool similar to a light bulb? I might think about this. I might think about this, okay? And so we learned that things that are better at allowing electricity to move have less resistance, like copper, okay? And things that don't allow electricity to move have a higher resistance, and those are like tungsten. And we measure resistance in ohms, right? Like ohm, but not quite. So that's the Greek letter omega, and this is the symbol for that. This is the symbol for that, okay? And last thing, the source. Everything has to have a source of where we are getting energy from. In this case, we're talking about batteries, okay? Batteries and generators are what give the energy, okay? So the coulombs come and get the energy from the source, right? And that energy is called a volt, okay? So that is why when you are reading something and it says a 9-volt battery, that is how much energy it is going to give a coulomb of charge. Each coulomb of charge will come to that 9-volt battery and get 9 volts of energy to then go give the light bulb. Okay. So I hope that this has been helpful. I know it's a lot of information that was just packed in there, but hopefully that's helpful. Remember, you can pause and use this to answer questions, come back to it, rewatch it, and do whatever you need to be successful. And remember, we are here for you. We have office hours, comments, and let us know anything else we can do to be helpful. Bye.